Good afternoon. Today I will present the proofs of two results. The first one is about geodesic spreading. The second is about the growth rate of distant circles. The first result says that if we work using normal polar coordinates and we define the function g of r to be the square root of the coefficient of the first fundamental form denoted by g, then we can make it become a smooth function on 0 epsilon, and most importantly, its third order Taylor polynomial at r equal to 0 is given by this function where the Gauss curvature appears. Okay, let's start proving that the function g of r can be extended to include r equals 0. This is done using the fact that sigma is the function defined this way, exponential map at p evaluated at r cosinus of theta e1 plus r sinus theta e2. This can be written as a composition of mu composite f, where mu is a function defined this way and f is the function defined by this formula. Then g of r can be written this way, sigma theta r theta 0. This is the derivative of sigma at r sigma 0 evaluated at the vector 0, 1. Why? Because we are considering the derivative of sigma with respect to theta. And now we use this fact and write the mu evaluated at r cosinus of theta 0, r sinus theta 0 of df evaluated at r theta 0 at 0, 1. This is easy to compute. The formula is here. We get the d mu evaluated at r cosinus of theta 0, r sinus of theta 0, evaluated at the vector r minus r sinus theta 0, r cosinus theta 0. And by linearity, we can factor out r. and we get this formula. This is a function which is smooth at r equals 0, and this proves the fact that if we set g0 equal to 0, then we get an extension of the function g of r on an interval which contains also 0, and it's clearly smooth because this is a linear function and consequently smooth, and this is a smooth function. Now we have to prove that the Taylor polynomial of order 3 is r minus r cubed over 6 times k of p. That is, we have to prove that g prime 0 is 1, g second at 0 is 0, and g third at 0 is minus the Gauss curvature at p. Okay, let's start by the first identity. This follows from this formula. This is the expression we found for g of r. So the first derivative, g prime, will be equal to the length of d mu r cosine theta 0, r sine theta 0, etc. But we know that the differential of mu is the identity map. Consequently, we get this identity. Instead, for proving the second one, we need to use theorem 5.26. That is this formula here, k equal minus square root of g second derivative divided by square root of g. This implies that if we set k of r equal k of r theta 0, g second r is minus g of r k of r. This follows from the fact that this is g of r. So g r is written using another notation as a g second of r, and this is g of r. So this is true for r in 0 epsilon. The reason why it's not true a priori for r equals 0 is that here you have a square root of g at the denominator, and the denominator gets 0 when becomes equal to 0 when r is at 0. We wrote before this formula, which says that g at 0 equals 0. And actually we define g this way to make it smooth. So we can extend it by continuity. Continuity implies the formula holds true also for r equals 0. If this is true, then we can evaluate both sides of this equation at r equal to 0, and we get that g second 0 equal minus g0 k at 0, but this is 0, so this is 0, and this proves the second identity. Now we have to prove the third one, and in order to prove this one, we differentiate star, where star is this formula, and evaluate at r equals 0. We get g second at 0 is equal to minus g prime 0 k 0 minus g 0 k prime 0. The second summand is 0 because this is 0, and the g prime at 0 is equal to 1. So we have that g second at 0 is equal to minus k at 0, which says that the third derivative, sorry, there is a typo, this is g third, which says that the g third at 0 is equal to minus the Gauss curvature at the points corresponding to r equal to 0, which is p. This is the end of the proof. So the next result I will prove is proposition 5.30, which is about the growth rate of distance circle. Essentially, this proposition says that the third order Taylor polynomial of the function which associate to each values of r nearby 0 the length of the distance circle centered at P is 2 pi r minus pi over 3 kp r cubed. So proposition 5.28, the one I proved right before, says that GR, so let's write proposition 5.28 ensures that G of R, this is equal to R minus R cubed over 6 Kp plus an error which depend on R and theta 0, having the properties that limit is R tend to 0 of the error function over R cubed, this is 0. Then if you want to compute the length of CRP, just integrate the function G of R, that is the length of sigma theta R theta 0 d theta, and if you do this you get 2 pi R minus 2 pi R cubed over 6 by multiplied by k at t plus the integral of the error function d theta, and if you want to find the third order Taylor polynomial of this function here, it is done. Just take the first two summands, because this one is an integral with respect to theta of a function which tends to 0 as described by this formula as R tends to 0. So this is at the end of the proof. Now, if you want to be more precise, you can prove that the first three derivatives with respect to R of this function tend to 0. Actually, R 0 if R is equal to 0. And this follows from this formula. And this says that the third order polynomial for this function is 2 pi R minus pi R3 over 3 times K at P. Now I want to talk about constant curvature surfaces. If surface is a regular surface has constant curvature, we can get a more precise result about G of R. Why? Because we can solve G second of R equal minus G R K R, and we get an explicit formula for G of R. This is what lemma 5.31 says. It says that the solutions the solution of G second R equal minus lambda GT with the with R, sorry, this is R, with R in at least in this interval, with the initial condition G0 equals 0, G prime 0 equal 1, R actually is, excuse me, 1 over square root of lambda sinus of square root of lambda R if lambda is positive. R if lambda is 0, 1 over square root of absolute value of lambda hyperbolic sinus of square root of absolute value of lambda R if lambda is negative. Lambda, of course, is a constant which represents the value of the curvature. The reason why constant curvature surfaces have some interest is that this proposition says that if you have two regular surfaces, S and S tilde, with the same constant Gauss curvature, then they are not isometric but locally isometric. Local isometric means the following. For every pair of points P and P tilde, respectively in S and S tilde, there exists a neighborhood O of P in S and a neighborhood O tilde of P tilde in S tilde such that O and O tilde are isometric. Let's prove this result. So suppose that sigma and sigma tilde are surface patches for normal polar coordinates respectively at P and P tilde. The reason why I wrote to you as a domain of definition of sigma and sigma tilde is that you can shrink, if this is not true, the domains of sigma and sigma tilde until they are the same. Then the first fundamental forms are F1 equal dr square plus g d theta square, and F1 tilde equal dr square plus g tilde d theta square. Now we use the hypothesis that the Gauss curvature of S and S tilde are the same. This implies that the function g of r is the same for S and S tilde. So g equals g tilde of r, and this implies that g is equal to g tilde that is the two surfaces have same first fundamental form. Then we can define a diffeomorphism F composing sigma tilde with the inverse of sigma, and this is a diffeomorphism which does the following. Sigma tilde can be seen as a composition of sigma with F. So in other terms, you get the surface patch sigma tilde composing this surface patch with F. So this means that F preserves the first fundamental form. Why? Because the first fundamental form of sigma tilde coincide with the first fundamental form of sigma, implies F is an isometry. And now we should take care of what is the domain of F and what is the image of F. On the blackboard I have that F is defined on V and takes value in V tilde, which which are not a priori neighborhoods of P and P tilde. Why? Because we are working with normal polar coordinates, and in the past we observed that when we work with polar coordinates, we miss the point which is the center of the new system of coordinates. I mean, the map, for example, sigma is not defined at r equal to 0, nor sigma tilde. So this means that V and V tilde are not neighborhood of P and P tilde, but you can fix this problem extending F to a larger open set. Precisely, you can choose to replace V and V tilde by O tilde, where O and O tilde are the images of the corresponding normal coordinates surface charts. Okay, this is the end of the proof. The next topic of today is the following: complete surfaces. In a few minutes I will give you the definition of complete surface, but I would like to announce anyway what is our main goal. Our goal is to prove the Hopf-Reno theorem. This is a global result, and it says that if a surface satisfies some conditions, then we can prove that there exists of a minimizing geodesic segment joining every given pair of points in a surface. So this result is much stronger than the result we saw before, because the results we saw before were about the existence of a minimizing geodesic segment inside a special normal neighborhood. Instead, here we are saying that I give you an arbitrary pair of points, and that you can conclude that there exists a minimizing geodesic segment. Let's start giving the definition. Five point 33. So let S be a connected regular surface. A sequence P1, P2 of point in S is called D Cauchy if if for every epsilon positive there exists capital N such that the intrinsic distance between Pi and Pj is more than epsilon for all ij larger than n. This definition is formally similar, actually identical, to the definition of Cauchy sequence for points in R3. The difference is that we use the intrinsic distance. So D denotes the intrinsic distance. What is the relation between being a Cauchy sequence and being a de-Cauchy sequence? Every de-Cauchy sequence in S is a Cauchy sequence. Why is this true? Because if this denotes the distance between Pi and Pj in R3, then this is more or equal to the intrinsic distance between Pi and Pj. So if you know that this distance here is more than epsilon for I and j larger than n, then also this one will be smaller than epsilon for I and j larger than n. And this says that the sequence of points P1, P2, P3, etc. is a Cauchy sequence. Now I can give you a definition of a complete surface. So proposition slash definition 5.34. So we have, as before, a connected regular surface then the following are equivalent characterization of what it means for S to be complete. One, every D Cauchy sequence of points of S converges to a point of S. 2. Every geodesic gamma in S can be extended to a geodesic on R. 3. For every P in S, the domain of the exponential map at P is all of TPS. This is the structure of the proof. We will prove that 1 implies 2. We will prove that 2 is equivalent to 3. And last, we will prove that 3 implies 1. Okay, so let's assume that every D Cauchy sequence of points in S converges to a point of S. Implies that every geodesic gamma, initially defined on an interval I, can be extended to a geodesic defined on R. Unfortunately, I have to erase. So proof of the fact that 1 implies 2. This is done by contradiction. So suppose that second statement is not true. Then we can say that, so suppose 2 to be false, then there exists a geodesic that I can suppose to be unit speed. Define on AB, for example, but not extendable to B. Some of you could ask the question, why the interval is this one? The reason is that it's possible to prove. So remark, if gamma is affine on an interval of this form, then it is possible to prove that it is extendable to A, B plus epsilon. The idea for doing this is that you can work inside a normal neighborhood of gamma B. You know that if you work inside a normal neighborhood centered at gamma B, then there exists a geodesic with the initial point equal to the given point and a vector, for example this one, which has a length non-zero in some interval, let's say length of V smaller than epsilon, and epsilon is exactly the radius of the normal neighborhood. So this says that if the geodesic stops at gamma B, you can extend it at least on an interval of length epsilon on the right. So the interval we will consider is like this. Now suppose that T1, T2, T3 is a sequence in AB converging to B, and this sequence is necessarily a Cauchy sequence, because every convergent sequence is a Cauchy sequence. We have that the intrinsic distance of gamma Ti to gamma Tj, because of the hypothesis of velocity vector of length 1 for gamma is more or equal to Ti minus Tj in absolute value. This implies that the sequence gamma T1, gamma T2, and so on is de Cauchy. By hypothesis, that is the fact that the statement 1 is true, it converges to a point P in S. Then let's use the argument I used before for proving that if the interval is the interval of the definition of gamma is AB closed on the right, then there is an extension. Consider a normal neighborhood O of P. We know that the geodesic gamma stops at P, so we can see this geodesic as a geodesic having initial point P. Exactly as before, I can extend this geodesic if I remain inside O, this way for example, and these contradict contradict with contradicts the fact that I am assuming that the geodesic cannot be extended. Now let's prove that 2 is equivalent to 3. The statement The statement 2 is the one about the extendability of the geodesic on the real line R. Instead, the statement 3, I want to recall it, is that the domain of the exponential map at P is all of TPS. The equivalence between 2 and 3 follows from this formula. If you have that V is a vector in TPS, then what happens if I use this identity and I replace V with TV? I can do, I can write exp PTV because 3 says that the exponential map is fine on all of TPS, so it makes sense to write down this, and if this makes sense, then this is gamma TV1. But we saw before that gamma TV1 is gamma VT. So this formula says that as soon as the right-hand side makes sense, then gamma VT makes sense. So this means that the gamma V is defined for any T in R. You can also use this idea, and assuming that the gamma Vt makes sense for every T, then you can prove that the exponential map is defined for any vector of the form TV. This means that TV can have any length in R, and this implies that the exponential map is defined on the entire TPS. Now let's prove that 3 implies 1. So I want to recall that the statement 1 was about Cauchy sequences. Precisely, every Cauchy sequence of points of S converges to a point of S. So let P1, P2 Cauchy sequence in S. So this means that there exists an integer n such that T Pn Pi is more or equal to 1 if I is larger than n. What is the meaning of this inequality? The meaning of this inequality is that for every I larger than n, the elements Pi of the sequence are contained in the ball B, defined this way. Now, we use the hypothesis, the fact 3, to prove that we can write B as exp Pn of V in TPS of length smaller or equal to 1. And we can prove that is compact. Why? Because this is a closed disk in R2 which is compact. And the exponential map is smooth and in particular continuous. So now we have a sequence the sequence of elements pi with I larger than n in B subconverges to a point of B because B is compact. So now we use the fact that a subconvergent Cauchy sequence is convergent and this implies that the sequence converges to a point of B. This proof shows that where is a point where we need Cauchy sequences because we need that we need to prove that a subconvergent Cauchy sequence is convergent. And this is the end of the proof, of course. Now let's show one simple example of a surface which is not complete, and then I will show a proposition which says that there is a class of surfaces which are complete. The plane from which we remove a point is clearly not complete. Why? Because it's easy to construct a sequence converging to the point you have removed. So this is a sequence which does not converge in the punctured plane. This is the proposition about complete surfaces. Every closed connected regular surface is complete. The proof of this result is immediate. Consider a sequence of points in S, which is de Cauchy. The sequence is also a Cauchy sequence. This means that we have convergence of this sequence in R3, but the surface is closed. This means that the limit points belongs to S, to the surface S, so the surface is complete. I would like to mention also a particular case of this result. Compact connected regular surfaces are complete. This is true because in R3 a compact set is also closed. And I will finish saying that there exist surfaces which are complete but not closed. So closed implies complete, but complete does not imply closed. Consider the surface parameterized by this map. With the ST in r times r. This surface is a generalized cylinder over a curve which is a spiral which converges toward a unit circle, precisely if this is the unit circle, then if you for a moment drop t and you look at the first two components of this map, you get a function whose image is the red line. Sorry, my picture is not very good. So it's a spiral converging toward the unit circle. And this surface here is the cylinder over this curve. So please look at the figure 5.13 in the book if you want to have a better figure. So precisely this surface is complete. For example, you can prove it using the fact that the geodesics are defined on R. The geodesics of this surface are vertical lines like this. They are straight lines, and the other geodesics are horizontal curves So it's difficult to make a picture, but imagine the cross sections of this object by an horizontal plane. The intersection is a geodesic. Instead, why it's not closed? It's not closed because it's possible to construct a sequence of points. So there exists sequence of points which are Cauchy but not de Cauchy, and for example this sequence here it's clear that this sequence is intuitively Cauchy, essentially, if you look at the distance between I and j, with ij enough high, enough large, then this can be made arbitrarily small. Instead, it's not de Cauchy, because you cannot make this distance, which is the intrinsic distance, that is the distance measured on the surface, arbitrarily small. The distance I am using here between these 2 points is the distance measured along this segment. The distance measured lying on the surface, that is the intrinsic distance, is the length of this curve. And I told you before that the red curve tends to the unit circle. So the intrinsic distance of Pi and Pj cannot be made arbitrarily small. So we have one example of sequence which is Cauchy but not de Cauchy, and this sequence converges to missing points because the surface tends to the unit cylinder, but it does not. The unit cylinder does not belong to the surface. Okay, so I think we can stop here. Next time we will prove the Hopf-Reno theorem. Thank you for your attention.